Hi, everybody. It's 10, so we'll get started promptly. It's my pleasure today to introduce Sophia Sanchez-Maes. Sophia came to Harvard after receiving her BS from Yale in physics and astrophysics. In her time as a PhD student in astronomy, she's studied plasmas throughout the universe from multiple angles, including theory, observation, simulation, and instrumentation. Early in her PhD career, she worked on analytic theory for direct collapse planet formation around black holes. Motivated by the desire to better capture the nonlinear processes governing accretion, Sophia learned how to use numerical simulations to model the behavior of magnetized plasmas. As part of this, she won a fellowship at the Flatiron Institute, where she used the Hammer code to study black hole accretion. And there she was analyzing properties of turbulence in one of the largest GRMHD simulations ever conducted. As Sophia gained expertise in numerical simulations, she learned not only about the plasmas that she was simulating, but about the architecture of the simulations themselves, in which she found many parallels with experimentation. And she had an interest in experimentation already from her personal experience as a builder and maker in her non-research life. And this led her to join a solar instrumentation project where she played a key role in building a soft X-ray CMOS camera and launching it on a suborbital rocket in a solar flare observing campaign. After the rocket launch, Sophia returned to simulation work in her final thesis project, a study of the influence of guide fields on flare spectra from Sagittarius A star. So a few accolades. Sophia is the recipient of an NSF Graduate Research Fellowship, a Ford Foundation Predoctoral Fellowship, an NVIDIA hardware grant, and the Templeton Theory Experiment Cross-Training Grant. She also won a Best Paper Prize from the SPIE. She's advised 6 undergrads in her time as a PhD student, and as an advisor, she's really a very caring advisor. On a more personal note, she's also really the kind of person who also cares really about her mentors. And when we would meet about her thesis recently and about her work before that, no matter how deep she was in the ordeal of producing a thesis, Sophia would find time to ask me about myself. We would often have kind of wide-ranging conversations inside and outside of science before returning to her work. And I really enjoyed them, and I hope that you enjoy her talk as much as I enjoyed our discussions. So without further ado, here's Sophia's defense presentation, Reconnection-Driven Flares in Magnetized Astrophysical Plasmas, from the solar atmosphere to Sagittarius A star.
Thank you so much, Jenna. Put the microphone on. Give me just a moment. Okay, is this better?
I think you may need to turn it on.
Right, okay. Are we there? Perfect. Thank you so much, Jenna, and thank you everyone for being here today. You mean so much to me, and I feel like I've been going on this PhD journey together with all of you in collaboration and community and fellowship, and I am just genuinely excited to share with you my work. During my time as a graduate student here at the Center for Astrophysics, I've spent just about all of my time thinking about one thing, and that thing is astrophysical plasmas. And I've been lucky to approach those plasmas from multiple angles, from instrumentation to computation, and across very different environments, from the solar atmosphere to Sagittarius A star. So today I'll be talking about flares, how they're powered by magnetic reconnection on the sun, and how I hope to convince you the same on black holes, and how we study them using both the tools we build and the simulations that we run. Across the universe, we see these sudden and explosive outbursts of light, flares, like this one emerging from the very heart of our galaxy around its central supermassive black hole. Now, Black hole flares, these sudden outbursts of energy, they emerge from this turbulent disk of plasma very near to the event horizon. And they can tell us a lot about how matter and magnetic fields behave in some of the most extreme gravitational environments in the universe. What you're seeing here in this visualization from Kaushik Chatterjee is a 3D visualization of the matter around Sagittarius A star, our galactic black hole. And it's based off of a high-resolution simulation that incorporates the physics of magnetic fields, of gravity, and of the plasma dynamics themselves. You can see that gas spirals around, swirling inwards towards the black hole shown at center. And it's colored based off of its density from purple to green. Some of this material is ejected in these narrow jets traced out by these magnetic field lines. And these field lines are kind of tightly anchored into the event horizon of the black hole here. You can see the disk itself is incredibly chaotic. It's filled with turbulent eddies, and as magnetic field lines snap and reconnect, they act to heat the gas, creating these bright hot spots that you see in red. They're a potential source of the X-ray flares that we observe on Sagittarius A star. Now, let's take a look at the flares we might be a bit more accustomed to on the sun. These flares are seen in the extreme ultraviolet using the atmospheric imaging assembly on the Solar Dynamics Observatory. You can see that these images reveal quite a lot about the behavior of flares. Unlike on black holes, we see fine, detailed structure that defines these flares because the sun is so much closer to us. You see hot magnetized plasma is moving in these loops and arches throughout the flaring plasma. And so we're not just seeing the spike in brightness from before. We see the full structure. We're seeing plasma that's being heated to tens of millions of degrees. We're seeing it flow along these magnetic field lines, and we're seeing the flare evolving over time. And so this kind of gives us a powerful picture to start with, revealing that the energy is released in light, released in heat, released in particle acceleration, and that the plasma responds to all of it. But the story doesn't end at the sun. The energy in the particles that are released when these flares occur can travel across the solar system and eventually impact us at Earth, where they interact with our magnetic field on our planet in really spectacular ways. Like here, you see these stunning aurorae in imagery taken from the International Space Station. These are just the visible aftermath of these high-energy particles from the sun exciting atoms in our atmosphere and creating these beautiful displays in green and red. But while aurora are very beautiful, they're just the visible and most benign sign of something much more destructive that's happening above our heads. Solar flares and the energetic outbursts that they often coincide with can impact our life and our technology here on Earth. When the charged particles reach us here, they can do things like damaging satellites or degrading solar panels, causing what's called single event upset on our onboard electronics, which is where a particle can flip a single bit in a computer's memory. These same particles pose serious risks to human life, to astronauts, but also to the crews and passengers on polar flights that go to kind of the Arctic and Antarctic regions. Closer to the ground, changes in the magnetic field can induce currents that could damage things like our infrastructure and our power grids, potentially damaging transformers or triggering blackouts. So clearly, understanding the physics and origins of flares is not just important for plasma nerds like me, it's also essential for protecting our technological infrastructure that we rely on every day. Now, understanding the impacts is one thing, but actually observing the events that cause them gives us a much clearer picture of how they unfold in real time. This slide shows exactly that, where we're seeing the type 2 radio burst that results from a very large, X class is the largest kind of solar flare, that was observed in New Mexico. Type 2 radio bursts are actually the signatures of shock waves, which move through the solar corona, often driven by the coronal mass ejections that go along with flares. And as these shocks are plowing through the outer atmosphere of the sun, they're emitting radio waves at progressively lower frequencies, which we can then detect here on Earth. And at the same time, the sun emits intense X-ray and ultraviolet radiation, which can literally change the structure of Earth's atmosphere, ionizing the outer layers and then causing a sudden radio blackout that you see here at the bottom. High-frequency communication, especially over the sunlit side of the Earth, can drop out completely as a result of these flares, as you see here. So clearly understanding flares both around the sun and around black holes matters both for life on Earth and for understanding some of the most extreme physics in the universe. But to understand these flares, we need to talk about plasma, because that's what the stars, the jets, the accretion disks are all made out of. We live in a plasma universe. Over 99.999% of all the normal matter that exists is in a plasma state. Plasma is kind of like a fluid, but not like the gas that you're used to, because it's made of highly ionized particles. Individual atoms have been stripped of some of or all of their electrons, and what's left are these freely moving charged particles, the electrons and the ions. Because they're charged, these particles don't just move randomly. They respond to electric and magnetic fields. And that's going to be essential for everything we discuss next, because magnetic fields play a central role in how flares form and how they release energy. Even though all of this plasma may sound very exotic, you are in fact used to plasmas in your everyday life, familiar with them from such phenomena as lightning, neon signs, or welding arcs. And these are just small-scale, less structured manifestations of the plasmas that we see in space. So if we want to play around in the world of space plasmas, we need to understand the rules. And the most important rule is this: the magnetic field sets the terms. Magnetic fields govern how plasmas move and behave. And here we see two powerful examples. Here you see Earth's magnetic field. It looks a lot like the familiar picture of a bar magnet. It has a north and a south pole. There's these invisible field lines that trace from one to the other. And these invisible strings actually act to shield us from the solar wind by channeling particles from the sun along these loops and into the aurora. On the right, the scale of the magnetic field is even larger. This is the Planck's view of magnetic fields threading through the disk of our Milky Way galaxy, shaping how plasma and matter are moving on even more cosmic scales. So magnetic fields in both cases, in all cases, act to organize, guide, and energize plasmas. So we know magnetic fields set the rules, but what exactly are they? Plasmas and magnetic fields are tight. They are linked together, tightly coupled through a property we call flux freezing. It means that in some environments where the magnetic field dominates, the field lines want to straighten. And as they do, they're going to pull the plasma along with it. So move the magnetic field, you're moving the plasma. And it's this property that we see so beautifully in the solar corona, where the magnetic field is so strong compared with the plasma that this glowing gas traces out the structure of the magnetic field lines. That's why these coronal loops actually look like illuminated magnetic structures. They're a diagnostic of it. The plasma is showing us the shape of the field, even though the magnetic field itself is invisible. Now, that's only one side of the story. In other environments, the plasma pressure dominates. Plasma flows shear and move and twist, and magnetic fields are carried along the ride, forced to stretch and contort in response to the plasma motion. This is actually what's happening in the very dense midplane of a black hole accretion disk. This particular simulation was led by one of my earliest mentors in graduate school, Matthew Liska, who really introduced me to the world of black hole accretion and general relativistic MHD simulations. So what you're seeing in this simulation is actually a slice through the midplane of the black hole accretion disk, with the black hole here at the center and the disk density shown in this rainbow color bar. At the very start of the simulation, you see no large-scale black poloidal field lines. But as material falls into the black hole, the turbulent plasma is dragging the magnetic field along for the ride, twisting and amplifying it in this dynamo process. And out of that turbulence, these strong poloidal field lines emerge, pointing up and down, storing magnetic energy that can later be released in very dramatic ways. So the magnetic fields that we're amplifying in the disk don't just store energy, they can also extract it. As the magnetic fields rise and thread the black hole itself, that twisting of the fields in the black hole taps into the black hole's spin energy. And the magnetic structure channels that outward, funneling plasma into these narrow, collimated jets that blast away at nearly the speed of light. So what we've learned from all of this is that flux freezing is our one unifying rule. Whether the field is guiding the plasma or the plasma is dragging the field, plasma and magnetic fields cannot escape one another. They are bound together, irrevocably, unchangeably, each shaping the other, until they aren't. Flux freezing is a rule made to be broken, and the breakdown is actually crucial. It's what my PhD is all about, because it allows this process called magnetic reconnection. Reconnection occurs when these oppositely directed magnetic field lines that have been stretched, twisted, or pulled together suddenly change their connections, creating new fields coming out at the left and right. In that moment, flux freezing has broken down. The field lines slip through the plasma, snap into new configurations, and fling plasma outwards as they release their stored energy. The result is an explosive burst of magnetic energy that is released to heat the plasma, accelerate the particles, and power the flares that we see on the sun, and as I will make the case for, around black holes as well. Now, in my time as a graduate student, I've been lucky enough to explore magnetic reconnection in two very different settings, the sun and black holes. But let's get started a little closer to home and talk about solar flares. Now, all this time, I've been showing you these really vivid images of solar flares in the extreme ultraviolet. And perhaps they look nothing like the sun that you're familiar with seeing, which maybe looks a lot more like the sun you see here at the upper left. This is the visible light sun, the photosphere, a lower layer of the atmosphere than the corona we were looking at before. During a solar flare, the brightness of the entire sun changes, as shown by these light curves superimposed on the wavelength channel of the sun in the picture. In each of these images of the sun, there's a flare happening at sun center, but you can see in the visible light, our net brightness actually decreases during the flare. Visible light, these cooler energies, are not where the action of the energy release is occurring. That happens at much higher energy scales and higher temperatures, which we see using specialized instruments, because our eyes cannot see this, in the ultraviolet and the soft X-ray. So each band is showing a different multi-wavelength view, but you can see that the one where you see the flare most starkly, where the contrast between the flare and the sun is most extreme, is actually the soft X-ray, where you see over time this very explosive, impulsive signature from the solar flare. So now that we've spent some time looking at the very detailed spatial structure of flares, it's time to think about how they present in time. Flares have a really rich temporal structure. In the soft X-rays, we see this fast, impulsive rise in brightness that lasts seconds to minutes, very quick, followed by a much slower decay that can last for minutes to many hours. If you look at these light curves from GOES, you can also see these things called quasi-periodic pulsations, little wiggles in the brightness that tell us that a flare isn't just a smooth one-time event. It's being continuously heated. And remember, these curves from the GOES spacecraft are just brightness versus time, the entire sun's brightness versus time. So there's no spatial information here. But even from this alone, we can see just how dynamic and how structured the flares truly are. So fast rises, slow decays, and even quasi-periodic pulsations that indicate ongoing particle heating. So we know solar flares to be powered by magnetic reconnection. But to understand how reconnection unfolds in flares, how it grows, how it evolves, how it dissipates energy, we need more than just light curves, which only show brightness over time. They're great for spotting variability, but they don't tell us anything about where in the solar atmosphere the energy is being released or what the structure of the flare looks like. For that, we turn to images. But therein lies the problem. Our current imagers are too slow to keep up with the cadence of this temporal structure illuminated by GOES, which gives us data points on the scale of single seconds, whereas even the Solar Dynamics Observatory only takes one full disk EUV image in a band every 12 seconds. So that means all this rapid variation we see in GOES is completely missed in the actual images. But even then, when we get an image during a strong flare, the physics often blows out the detector. The flare is so bright that the pixels saturate, they max out, and then start bleeding into adjacent pixels, causing these blooming, these little streaks that are coming out. So just when reconnection is at its most extreme and the impulsive heating is occurring, we're losing exactly the fine structure that we would need in order to understand it. And that's why we need something better: higher cadence, higher dynamic range, and clean, unsaturated images of flare evolution. part of the reason we're missing these detectors, this detail, is in the detectors themselves. Most of our space solar observatories use these charge-coupled device detectors, which have been the workhorse of space imaging for decades. They're incredibly sensitive, incredibly stable, but they weren't built to handle the speed and brightness of the largest solar flares. Now, newer technology, CMOS detectors, offer a very different approach. These are the same kinds of detectors we're all familiar with. They're in our phones, they're in our DSLR cameras, and they can read out much faster and handle bright signals without blooming. CCDs and CMOS detectors both use silicon to detect light, but they operate really differently. When solar X-rays encounter the detector, they liberate a cloud of charged electrons proportional to the energy of the incident photon. And so individual pixels on the detector then accumulate that charge, which we will read out and interpret electronically into something we can call data. Now, in order to do readout in a CCD, charges get shifted across the array into a single readout. But when CCD signals get too bright, the excess charge can spill into these adjacent pixels, where the barrier to entry has to be low for charge transfer. And that's what blooming is. Now, CMOS operate very differently. You can see here that there's that every individual pixel is able to read out, all the pixels are amplified in parallel, and every single column has its own analog to digital conversion. So CMOS detectors have much higher dynamic range. They can read out far more quickly. They require a lot less power. And they also require less cooling, all of which make them really well suited for observing flares as they actually unfold. So with that, how do we get beyond the limitations of the existing imagers and realize the potential of these CMOS cameras? That was the purpose of the first project that I worked on in my PhD, where I was able to collaborate with this incredible team of SAO engineers to build this new kind of fast soft X-ray CMOS camera, reading out quickly to resolve the spatial and the temporal structure and prevent saturation using a new technology, which are called these back-illuminated delta-dope detectors that have a pixel design which prevents blooming. So exactly what we need if we could make it work. I then had the opportunity to lead a mission in collaboration with my co-PI, Chris Moore, that put this camera onto a telescope, transforming it into a complete instrument ready for science. Finally, this flight was actually part of NASA's first ever solar flare sounding rocket campaign, which was this collaborative mission that brought together many different novel instruments aboard 2 different sounding rockets, which launched simultaneously on the same solar flare, aiming to create the most comprehensive set of observations yet recorded on a single flare event, which was incredible to be a part of. And you'll hear about that now. So I am so grateful for this amazing CMOS team that I worked with at SAO. They're the ones who made all of this possible. A project like this, engineering a camera based off of brand new sensor technology and going from bench to space in just 2 years, takes a huge collaborative effort. And I really want to shout out Central Engineering, who are absolutely essential. They helped turn this camera from an idea into working hardware. And I think as astronomers, we all owe our engineers everything, because without them, we have no data, we have no instruments, we have no knowledge of anything going on in the universe. And so please, today, if you take nothing else away, thank your engineers. And last but not least, I do want to acknowledge again my co-PI, Chris, for his leadership and partnership throughout this entire project. So we engineered a camera. This camera. This diagram shows the Saxy rocket CMOS camera that was designed for this mission. You can see light would enter from the right through this aperture to hit the detector. The detector and the electronics are cooled by this passively by this cold finger here to keep the performance stable while it's on the rocket launcher. But after the detector gets the signal, the electronics handle the job of reading and digitizing that signal. We have an analog board to control and bias the detector, digital one that manages timing and digitization, and back-end to handle data transfer and power management. And all of this works together to get these high-cadence, high-dynamic range images from the detector all the way down to the computer and then to storage and later analysis. So engineering a soft X-ray camera takes a lot of steps, which I will not show here. But I want you to appreciate that it is not a clean process at all. Here you can see some of the electronics being designed, FPGA wiring diagrams, high-speed data lines and ADCs, and all these pieces have to talk to each other at just the right speed in order to make the magic happen. As part of this project, we developed 4 custom circuit boards in-house, power management, analog control, digital control, and power delivery and computer interfacing. And on top of that, we integrated a commercial single-board computer directly into the system. All of the parts that we incorporated had to be safe for space, able to handle the temperatures, the radiations, and the vibration and launch conditions. But at the beginning, the images that we got back looked like very scrambled puzzles, proof that the system was getting the signals, but not yet putting them together in exactly the right way. But as we debugged, we started to see real light signatures, like with this early test image of an LED light strip on our detector. From there, we moved into full functionality testing. You see the camera set up in an electromagnetic interference box, wires everywhere, lots of probing, and eventually we reached a stable system that was ready for science. Now that we have a basically functional camera, we want to better understand how it responds to light. To do that, we try and control everything we possibly can about our test setup so that any variations that we detect with our camera are intrinsic to the design of the camera and not some variations in the stability of our light source or the flatness of our field. And so we use this integrating sphere in order to flatten the light from our very stable quartz tungsten halogen lamp. And this flat field of light kind of illuminates not only our detector, but these reference detectors. In every setup we have, we do not trust whatever it is our newly engineered camera is telling us. We have to confirm with detectors that we do trust, in this case, calibrated photodiodes. So in this setup, we slowly turned up the light. And here you can see the response of the Saxi CMOS camera to 10 different levels of incident illumination in the visible light spectrum. And all of the data here was taken in the lowest gain setting. You're seeing the good pixels and the dead ones. With all of this information, we're able to calibrate the camera and understand things like linearity. So linearity is this fundamental property we look for in all of our imaging detectors, and it just means that when we put in more light, we get proportionally more signal out on the other side. CMOS detectors are hard because by having readouts on every single pixel is basically its own detector and should be treated as such in all of our calibration and analysis. And so a lot of the work that I did on this detector was trying to understand and model this pixel level behavior, not just in terms of signal like here, but also in terms of its noise characteristics. And the not only physical patterns that show up on the detector, but the logical ones that have to do with the electronics and how and when they're being read out in time. So you can see that at the end of the day, after much calibration, we were able to show linear response with our camera through both the high gain and the low gain mode. The color bar shows in black and white are showing kind of how densely the pixels are clustering in this space, revealing kind of the bulk and the outlier pixels that exist. And so after we get this information, we want to better understand these pixel-to-pixel variations by understanding the noise. So in response to a given level of illumination, what is the mean of an individual pixel taken through many different snapshots at the same illumination level? And also, what is the standard deviation of that pixel to the same exact signal? And so that kind of helps us understand how noisy this pixel is, but also the evolution of a plot like this helps us understand temporal patterns in the response of pixels as the readout is rolling through the camera, which was really interesting. Plots like this help us to diagnose patterns not only from the physical subarrays of our detector, but the logical ones. And that was a really cool process. So we built this camera to study flares, which emit in soft X-rays. But up until now, all of our characterization has been done using visible light. Now, X-rays, thankfully, don't make it through Earth's atmosphere particularly well, which is good for us and our continued health and safety. But that does mean that we can't test our camera under normal conditions here on the ground. We have to go into an artificial vacuum if we're not in the vacuum of space. This is a diagram of the X-ray calibration facility here at the CFA. And this is a special lab, kind of a legacy from the Chandra Observatory that was built here, that lets us generate controlled X-ray beams, which we will then kind of illuminate our camera and see how the camera responds to those beams. The setup starts on the left with something called this Manson source. And inside of the Manson source, a beam of electrons hits a metal target in order to produce X-rays. And identical beams are coming out of both arms of this detector, one towards the short arm to our reference detector. Just like before, we have a detector that we can trust a bit more than our camera, this gas flow proportional counter. And on the other side, one goes to illuminate our soft X-ray CMOS camera. Everything else aligned here as precisely as we can. Distances from the source to the detector are measured so that we know exactly what the camera is seeing and how the signal of the camera would compare to the signal seen by the gas flow proportional counter. And so this is important. We're not just collecting images with this camera. We're trying to understand how to turn them into physical measurements of solar X-rays. And so we spend time understanding how the camera responds to different energies of X-rays from different sources and targets within the Manson source. So this slide is actually super exciting. It shows a very unique property of using CMOS detectors in the soft X-ray regime. So what you're looking at here is a histogram of the X-ray emitters, the X-ray energies that the camera is detecting in response to these various characteristic lines that are being produced by the Manson source. This helps us diagnose things like the spectral resolution of the camera, absolutely. But just the fact that we get a plot like this itself is actually quite revolutionary. It speaks to the nature of how silicon detectors are able to imbibe and interpret the signals from X-ray light. Because of the relationship between the silicon band gap and the energy of these soft X-rays, every individual X-ray photon liberates a charge of electrons proportional to its energy. That means that a CMOS detector in the soft X-ray is not only an imager, but also, if read out fast enough, can also give us spectral information. This means that by pushing towards this high cadence horizon and reading out these detectors as fast as we can, we hope to someday create a future where we are reading out the signals from individual photons and thereby creating pointillistic images where every photon has both an energy, a spatial location, and a temporal location. And that would allow us to actually watch reconnection unfold in space, in time, and in temperature, which would be incredible. So we have a camera. It can respond quickly to soft X-rays. And the next step is to build a full instrument around it, something that we could actually fly to observe the sun during solar flares. And this is the Swift Solar Activity X-ray imager. This diagram on the bottom shows the full optical layout from left to right, where kind of light first enters through this external baffle, which helps block stray light. It passes through an entrance filter that helps prevent unwanted light from getting to our camera. As we saw before, our camera is sensitive to visible light and other things, so we want to make sure that the only light that makes it to our detector is the soft X-ray light we're actually interested in scientifically. And then it passes through other filters that kind of continue to reject all the non-X-ray light. But I think most important addition to all of this was our Walter 1 grazing incidence X-ray optic. In order to create images of the sun and not just get individual energies from the photons, we need to be able to focus the signals that we're getting onto an image on the detector plane. And for that, I want to thank our amazing collaborator and optics lead, Suzanne Romain. Suzanne's Romain's lab here at the CFA is responsible for fabricating, diagnosing, characterizing X-ray optics for myriad space missions, but also lots of missions here on the ground where they're used in lots of particle experiments. So in this photo montage from our optics effort, I'm showing the optic itself, which is called a Walter 1 optic. Basically, X-rays are really hard to redirect. They have such high energies that they resist being modified in their path even slightly. If you try to turn them around too much, they will just absorb through the material and you will lose them. And so all of these X-ray focusing optics operate on this principle of grazing incidence, that just like skipping stones on a pond, you can move the move the X-ray very gradually as long as you're throwing everything basically parallel to the surface that you're bouncing off of. And Suzanne Romain's lab was able to fabricate these optics custom for us in-house through their miniature X-ray optics program. And I kind of entered the process at the diagnostic stage, where I was able to travel with Suzanne and JSUB to the Marshall Space Flight Facility, where we had time on their 100-meter X-ray beamline. There we were able to take all of the optics that were created from this effort and evaluate their point spread function, their energy profiles, and even try and diagnose some of the physical changes in their structure, which we can see hints of at these like intra-focus images of the detector, where you see the structure of the physical spider that was put onto the optic in order to attach it to the rocket, for example, in these white spokes. So through this process, we were able to understand how the optics performed and also understand how the performance changed, comparing their performance on the second run at the beamline to the performance at the first, before we had applied this mechanical structure that links it to the rest of our telescope. This is me actually inside of this beamline, which is truly enormous, alongside the SAXI optic, which is mounted on this hexaposit for testing. So, delivering a spaceflight instrument like SAXI is not a straight line. It's a very nonlinear process, lots of moving parts, lots of moving people, and that means that we have to coordinate across various teams. We went from optical design and fabrication to mechanical integration and alignment and thermal and electronics and management and testing and documentation, so much documentation. And every step just depends on the others working. And so I just want to thank, again, the teams not only on the SAXI instrument, but on all the instruments that were on High-C rocket, which was the rocket that we flew on. This is the team that delivered High-C. And I just want to emphasize again that, our opportunity to launch was as a ride-along on this other rocket called the High Resolution Coronal Imager Flare mission. And we were there alongside several other instruments, the Kool-Aid mission and the Capri Sun photometer that gets really fast flux signals. And so I guess we were the only ones that didn't get the message, name ourselves after a sports drink. But we go on. So we had this incredible opportunity. We were one of 4 individual instruments on this one rocket, and we were not the only rocket that flew through this campaign. In this campaign, 2 rockets blasted off simultaneously on the same flare, each loaded to the gills with as many instruments as they could carry to create this very comprehensive data set. And that brings us to Alaska, where eventually we were able to ship our instrument and our rocket after doing lots of calibration, bending, balance, vibrational testing at White Sands in New Mexico. And there we sat for 2 weeks. Our rockets readied on the launch pad and waiting for the flare that would give us the signal that we were so hoping for. We were in Alaska specifically so that we could launch at a moment's notice. But what I wanted to illustrate here through this diagram of all the solar X-ray flux throughout our entire campaign launch window is just how much of a miracle it is we got a flare at all, even though we were sitting on the launch pad for 2 weeks. Because throughout this 2-week period, we weren't actually ready to go every second of it. People have to sleep and take days off after working, all the time for so many days. And of course, things happen that are completely outside of your control. The winds aren't right. There are hikers or bears on the launch pad. Alaska things, And so I show here in these kind of gray illuminated bars the opportunities we actually had to launch. These are moments where we could have pressed the button if the flare were to occur. And you see that there's not that many of them. In the entire course of the campaign, we had maybe 8 opportunities. And within those, you really don't see us getting lucky for much of it. We finally got our flare on the very last day of our campaign, which is incredible because in Alaska, fire season and hunting season would have meant that we would have to wait a great many months before trying again. So we got very lucky. We saw this flare, this M-class solar flare that we launched on. You can see the flare classes here delineated on the right, where these excursions up here would be things that we would be able to perhaps launch on. And I just was so thrilled that we not only had the opportunity, but we were able to get data from that opportunity. SAXI rocket did record high time cadence measurements of solar soft X-rays from this M-class solar flare. The analysis of this from our instrument and others within this campaign is ongoing, but I think we all have a lot to look forward to in terms of what we can see scientifically from this very comprehensive picture of solar flares. Now, I've thanked my team so many times, and it's still not enough. Here I just wanted to emphasize just how uncountable and unnameable the number of individuals involved in a mission like this is. This is just the subset of the team that came with us to Alaska that spans across institutions. On our High-C rocket, we had NASA headquarters, NASA Marshall, Montana State, which provided this photometer, and us here at the Center for Astrophysics, who worked on 3 of the instruments on this rocket, including SAXI. So in this project within my PhD, I think we've set the stage for a future where we can actually get spatial spectroscopy and learn more about reconnection in that process. We developed a novel CMOS camera using these delta-doped back-illuminated detectors that had never gone to space before, and created an instrument that combines speed, sensitivity, and the spectral potential. We went from bench to space in 2 years. During the High-C rocket flight, we actually captured sub-second soft X-ray emission during a flare, proving that our imaging is possible and flight-ready. And we also advanced the key technologies involved to TRL 6 or 7, which not only supports future solar imaging missions, but also astrophysical missions like the Ultraviolet Explorer, which is using the exact same detector technology in their upcoming mission. All of this aligns with the goals of the Heliophysics Decadal Survey, which specifically calls out the need for high-cadence solar soft X-ray observing to study flares and to understand reconnection. Because if we want to understand these big questions, like where is the energy released, how is it partitioned, and how reconnection actually unfolds in space and time, this is how we get there. And I'm so excited to have been just a small part of it. So let's move on. Flares don't just happen on the sun. They also erupt around some of the most extreme objects in the universe, which are black holes. And just like on the sun, we think magnetic reconnection could be powering these flares also. So now let's talk about the black hole at the center of our own galaxy, Sagittarius A star. Now, Sagittarius star is pretty quiet as black hole goes, but every so often, maybe statistically once a day, it lights up with a flare in the X-ray and in the infrared. So you can see in this image the difference between the non-flaring Sag A star and the Sag A star during the brightest flare that was ever recorded, where the flux increased by over 600 times. And you can see, even with our eyes, the signature of this specific flare. Patterns emerge within the flares that we have observed from Sagittarius A star over the past decades, and that's that X-ray flares always seem to coincide with infrared flares. You never see an X-ray flare without one. But infrared flares often occur on their own. So a question is, what's driving that? Is reconnection still at play when we see an IR flare? And how do physical conditions like the magnetization of the plasma and the field geometry and energy injection affect what we're observing? So I just want to take a step back and say that when we observe flares from Sagittarius A star, we are not getting these detailed, spatially detailed images like we do for solar flares. In fact, in many cases, for the infrared and the X-ray, Sag A star can be a single or a group of otherwise unresolved pixels. But that doesn't mean we're missing detail within our story, because what we do have is this rich spatial and temporal signature. And this summary plot of the spectra as a function of kind of different energies from the X-ray and from the radio and submillimeter to the infrared, all the way to the X-ray signatures on the right, shows us just how this structure changes from the non-flaring Sag A star to your average X-ray flare to the most powerful X-ray flare that was ever observed. So yes, although we don't have a pretty picture, we do have a highly diagnostic one. And this is exactly where theory and simulation become indispensable and powerful tools to give us the picture that we have the potential to create from this data, connecting one pixel light curves to the underlying physics of reconnection and flare production. So now that we have these very hard-won data points, it is upon us to try and interpret them. And we do that using physical models and trying to see what fits. So this work by the Gravity Collaboration shows that maybe this model is not the best fit, but we try again. A little better, sure. And this one looks great. But the story doesn't end there, of course. Once we have a good fit model, we have to understand what that model means for our system, and then go back to the observations to see what those have told us about how the system must behave to evaluate whether or not that model fit has any physical interpretation or veracity. So let's talk about two different fits that seemed good enough for this Sagittarius star flare. In the first fit, synchrotron self-Compton, it asks something big of us, and it asks a big thing of our densities. This model requires densities that are much higher than the densities we know to exist on Sagittarius A star, which maybe disfavors it. So we go to the second model that fits fairly well, which is this cooled synchrotron model. It also asks something very significant of us. It asks acceleration that might strain our credulity, requiring electrons to be accelerated to Lorentz factors of 10 to the 5 or 10 to the 6th continuously throughout these flares. A lot of the literature that discusses this process appeals to the presence of some unknown motor, which powers the continuous acceleration of these electrons throughout the flare. And it is the purpose of my PhD research to clarify the nature of this unknown motor once and for all. So through this theoretical project, I will discuss lots of different components, identifying the mechanism of this unknown motor, putting it in a global context of the black hole accretion disk, and finally conducting kinetic simulations to show the correspondence between the spatial signatures, the spectral signatures of our observations, and the power spectra of particles accelerated through the reconnection process. So you want to accelerate some electrons. Whenever we have to accelerate electrons in space, we usually turn to one of three typical culprits, those being shocks, magnetic reconnection, and turbulent heating. Now, shocks are not consistent with the regularity of the flares that we observe, but turbulent heating could be. So the first thing that we do is evaluate whether or not this hypothesis could be describing the physics that we see. What we find when comparing the relevant timescales for turbulent heating against the timescales of synchrotron cooling, which acts to take down whatever turbulent heating is putting up, we find that turbulent heating is insufficient to accelerate particles to these X-ray emitting energies because turbulent acceleration cannot catch up with cooling in these regimes. Oh, that's wide. Turbulent acceleration can't catch up with cooling in these regimes. So what this means is that turbulence alone is insufficient to explain the signatures of X-ray flares from Sagittarius star. It's certainly a part of the system and a part of the process, but it is not in and of itself the answer. That leaves us with magnetic reconnection. And to understand how this operates in a black hole environment, we have to turn to the global dynamics of the accretion flow to try and understand where the reconnection could be occurring. In GRMHD simulations, like these ones, conducted by Bart Ruperta and Matthew Liska, which I had the good fortune of being able to analyze myself while a student at the Flatiron Institute, you can see the formation of plasmoids and X-point-like structures within the GRMHD accretion flow. These are exactly the sites where reconnection could happen, but GRMHD simulations are unable to tell us about the detailed physics of the particle acceleration itself. For that, we have to turn to more kinetic modeling. But this simulation kind of gives us an idea of where and when and how this could potentially be happening. So let's talk about that in more detail. In these accretion flows, we have a disk of plasma that wants to move onto the black hole, falling into its gravitational potential well. Like we discussed before, the plasma is woven through with magnetic field lines, like the ones shown here in green, toroidally sweeping through the disk plasma. Now, black hole accretion flows have the interesting habit of accumulating these pink magnetic field lines, these poloidal field lines, very near to the event horizon of the black hole. And this sets the stage for our potential environment for reconnection, where this toroidal field line is forced to move with the plasma that is accreting onto the black hole. The plasma goes unstable via magnetic Rayleigh-Taylor or some other process and creates this kind of pinch situation where this once coherent and single field line is forced back on itself into a configuration where we now have oppositely directed field at this juncture, and that can create reconnection. So the black hole geometry itself will repeatedly set up the conditions for reconnection as a function of just the ingredients that we have put together. The other important thing to note here is that all of this reconnection would be happening in an environment with a strong, coherent guide field, this poloidal field that's always building up at the horizon for us. And so it's this geometry that we're going to emulate within our particle and cell kinetic simulations to try and understand if something like this could be responsible for the flares that we've observed on Sagittarius star. So as you can see in this tortured schematic, I tried to emulate exactly these conditions in this particle and cell simulation, where there's a strong guide field oriented here, reconnecting magnetic field oriented there, a current sheet that's doing all of this reconnection, and some boundary conditions that hopefully allow this to act like a small chunk of a larger system. So now that we're oriented into our exploration of reconnection within strong magnetic field in relativistic environments, I wanted to show you what one of these simulations actually looks like. So here I'm showing density in this color bar where yellower is more dense. And you see these thin magnetic field lines tracing along. The very beginning of the simulation starts with this Harris current sheet that goes into this initial transient. But after that, you see something more steady state develop. And the plasma fragments into smaller structures, flux tubes and current sheets that are wound around with magnetic field, kind of helically wrapping these things that we call plasmoids or current sheets, especially at these later times, once the simulation becomes more stable. So I ran simulations like this across myriad conditions, across conditions where there was no guide field, all the way to conditions where the guide field was dominating the dynamics. And the results of that were really interesting, and we're able to compare those to the spectra that we observed from Sagittarius A star. A few lessons are clear from this. One is that at very low to no guide field, the particles are able to accelerate to really high energies. The maximum particle energy is very large in that case, whereas where the guide field is very strong, your maximum energy is far lower. This creates a potential explanation for why sometimes you would have an infrared-only flare if you're just not accelerating your particles to high enough energies to justify an X-ray one. But we also saw that even amongst X-ray flares, we see different slopes that correspond to different brightnesses of X-ray flare that we've seen. And we see that we can reproduce similar slopes in the X-ray analogous component of our simulation, where we show P of 2 and P of 3 corresponding to the case of the maximum brightest X-ray flare versus an average X-ray flare, which can modulate as a function of this magnetic field. Now we can extend this by understanding that we get more particle acceleration as we increase the size of our box, by understanding the trends as we increase our magnetic guide field. And in future, we hope to do exactly that, continuing and extending our simulations, running more of them in order to create the parameter space survey that will allow us to trace out general relativistic MHD simulations, which give us this global context of the entire black hole disk, and using these particle and cell simulations in order to inform the emission models utilized to ray trace them, which will create these really comprehensive, close pictures that we can compare to our observations and better understand the nature of the physics, and hopefully explain some things like the timescales observed in infrared versus X-ray flares, because infrared flares happen many times a day statistically, and X-ray flares are less common. It's also interesting to note that the guide field dependence of whether or not we would expect an X-ray or infrared flare could also make polarization measurements a really interesting things to pursue, whether in the infrared or in the X-ray someday, maybe. And last but not least, understanding these flares better helps us use those flares themselves as a diagnostic of the closest regimes to the black hole. I know we all know that these close-in star orbits have allowed us to show that the black hole itself exists, but these flares happen even closer, very near the event horizon. So if we really have a good handle on the physics of their occurrence, their existence, their properties, and their orbital parameters can tell us something about the behavior of matter in magnetic fields in very strong gravity. So just like experiment, theory does not happen in a vacuum. And I wanted to thank the entire team of people that I've worked with since very early in grad school, especially my theory advisor, Sasha Filipov, who I've worked with since 2022, Bart Ruperta, who is my go-to on some of these GRMHD simulations to this day, and the entire team of students, postdocs, friends, and collaborators that are never far away. I also want to thank Sasha Trinoglasov, who was a great help to me in running these particle and cell simulations, and Braden Gale, who's really carrying the torch of these MHD simulations to understand the global structure and environment in which these flares occur on black holes. Last but not least, I want to thank this entire collaboration we have that has welcomed me, which is this Sagittarius star flare collaboration, many members of which are here at the CFA. I'm so lucky to be part of a theory environment that collaborates so closely with observers and with instrumentationalists. And I think this is a real statement about the kind of science that I hope to do throughout my career, which is very integrative, very collaborative, and engaging always in conversations between theory and observation in all things. So throughout my thesis and throughout this talk, we've been able to talk about magnetic reconnection in these very different environments, from the sun to Sagittarius A star, building the tools and using our simulation tools to hopefully further our understanding of magnetic reconnection and flares. And with that, I want to thank my funding support, as well as acknowledge the land and the people without whom none of this would occur, because Harvard University is located on this traditional and ancestral land of the Massachusetts people, which is itself sacred. I wanted to thank my thesis committee, who've been here with me through so much, and especially my external evaluator, Jim Drake, who traveled all the way here to give me comments on this thesis, and who I'll be seeing a lot more of next year when I'm working with Sasha Filipov just down the hall at the University of Maryland. I wanted to thank many people in the Harvard Astronomy Department, but especially Mark and Peg, who are just the lifeblood and the beating heart of everything that happens in this graduate program. I want to thank various people that I've learned so much from in the department, especially our theorists, Avi Loeb, who was one of my first advisors, Ramesh Narayan, who I learned so much about Sagittarius Star and the Galactic Center with at the BHI, and Lars Hernquist, who was a huge support and mentor to me throughout my PhD. I also want to thank my mentors, who who are everything. Tom Garan, who was with me throughout the entire process of building SAXI every day in the lab, electrical engineer extraordinaire. He is incomparable. Mari Paz Miralles, who welcomed me into her home, made me feel part of community, and who's been through all of this with me. I have so much thanks to her. And Dave Thoreau, the most brilliant genius in this place, who I love so very much, and I hope to be just like him one day. He is our fabricator, welder extraordinaire, and solved many of our engineering problems with us on SAXI, always collaborative, always willing to take on a problem, a crazy measurement, comes back the next day with such interesting ideas. Just like, I get so much energy whenever we speak. And also Karin Oberg, who has just been a light to me, showing me kind of the scientist that I want to be, a real personal role model in so many ways. And I'm so thankful to her for being the chair of my committee and for making so much time with me throughout my PhD. I want to thank my advisor, Jenna Samra, who is also a role model to me. She is an engineer, she is active in her lab, she is kind of very hands-on in the way she runs her projects, and I really admire all of it. She is brilliant. She has so many interesting instruments that are happening to just chase these solar eclipses and better understand the corona. And I really, truly hope to continue in our conversations about the sun for many years to come. Thank you to my theory advisor, Sasha Filipov, who I've been working with since 2022, and who has just kept the door open to me throughout that entire time as we went from thinking about the GRMHD simulations to the PIC ones. There are too many people to thank here, but so many mentors that I've worked with scientifically, personally, have gotten me to this point, and I just really have so much gratitude. So thank you to my friends who've gotten me here, especially Osase Marie, who's been here with me since undergraduate. We've kind of walked this astronomy journey together. She is now a doctor herself, and I'm so proud of her. and Alejandra Corona Ortega, who is my best friend and who is always here to support and be with me through good times and bad. My family also has too many people to name, and this is just a subset taken at a recent event. Actually, my cousin Daniela's wedding, I wanted to specifically shout out her and her husband Nick, who live here in Cambridge and have just been huge supports to me throughout my time in graduate school. I'm lucky to have married into an amazing family with the Sagittarius, and they have also given me so much love and so much support. Ali and Milad also live locally and just have been incredible supports to me as I've gotten through grad school. Faye, my mother-in-law, is also really amazing and has been so loving and so supportive to me, so I thank her. And also my cousins, my family, my aunts, my uncles, just some of whom are pictured here. Victoria, Greg, Rebecca, my tia Tina, Monica, and then Daniela and Nick again. I want to thank my grandparents, my grandma Rose, and my grandma Christine and my grandpa Albert, who are just incredible examples of what it means to kind of create home, create community, and to do all things with great love. Thank you to my sisters, Catalina and Mireia. I just truly cannot imagine growing up with more incredible people who are both so wonderful in their own right. Mireia specifically was here with me throughout most of my time at Harvard since she was an undergraduate student during my PhD. And I have so many fond memories of just like having the best time with her late at night or, you know, being the loudest people at the Harvard pool laughing and talking throughout our swims. I want to thank my parents, Margaret and Jim, without whom none of this would be possible. They have been such incredible supports to me through everything. And I love them so much. Finally, I want to thank my partner, my husband and my greatest collaborator, academically and in life, Andrew Sagery. He's also an astronomer and got his PhD right here just a year ago. And I look forward to continuing building a life and exploring the universe with you for a long time to come. And so with that, I ask for questions on this work that encompasses instrumentation, mission, and theory as we learned about the reconnection of flares across the universe.
Thanks, Sophia, for a really nice talk. So we'll open up to questions, and Andrew has the mic if you want to run it. Chris.
Got a few comments. Can you go to slide number 20? So you made a comment earlier about the visible light, just some information. The dip in the intensity is mostly due to the active regions having less intensity than the surrounding areas of the sun.
I understand that.
For larger flares, there actually is an increase. H-alpha flares, white light flares, etc. And then I have a question on slide 43 or 44. Could you go to that, please? You talked earlier about our CMOS cameras are all in our cell phones. They're front side illuminated. Special processing 44.
Yes, this was the backside illumination processing that I mentioned. Where
Can you go to slide 44, please? Yeah, thank you. You were talking? You were speaking?
No, just that the CMOS cameras we use in the soft X-ray regime actually differ from the cameras used in our phones in very important ways. Specifically, the CMOS cameras of our phones have a lot of electronics that would otherwise kind of absorb or impede the soft X-rays on the way to readout. So rather than being front side illuminated like those detectors, these are backside processed, which allow the photons to kind of be detected in a way that is unimpeded. Yeah,
thanks for that explanation. So my question is, the name delta doped, I'd like to hear about how is that unique to the backside processing to make this detection in soft X-rays actually possible? Because like you said, on the front side illumination, it's hard to do.
Yeah.
And how does that affect what we see here in terms of the shapes? They're not like delta functions. They have like some structure to them.
Sure thing. So delta dope detectors are a kind of processing where within the silicon is a crystal. That crystal can have different impurities, different defects that could otherwise trap charge signals that could then be released at later times during the readout. And so this kind of natural function of the silicon can create situations with other backside processing that would generate what's called like quantum efficiency hysteresis, where the same signal that is incident on the detector can create different signals that we read out of the detector because of these impurities. Delta doping is a process that kind of tries to fill in those gaps so that we don't end up trapping this charge and creating these hysteretic situations. So I'd love to open it up for more questions.
I forget the slide number, but you had a beautiful movie simulation of reconnection that started off with sort of two cylinders going off on left and right sides. And
Two cylinders on the left and right sides.
it was near the end of the talk. So
Okay.
the Sagittarius star simulations.
Ah, yes. Yes.
And while you're finding it,
Is this one?
around there, back and forward, is the movie.
Oh, okay.
There we go. That was it.
Yes.
Right.
Yes.
Two cylinders going back. What again? You were saying that this eventually hit some sort of steady state or close to it, and my question was: A, I didn't quite see that, but B, because you're looking for flares, would you expect to see a steady state, or do you expect to see more like quasi-steady state?
That's such a good question. So I think this kind of speaks to the difference between the scales that we're thinking about in global simulations of flares versus in these very local kinetic boxes. So what I wanted to mention is that this box is just kind of something smaller than a pixel in a GRM HD simulation. So this box is specifically constructed to create reconnection, and the time signature of this entire box is so much shorter than even a single time slice of what's happening in the larger GRM HD simulation. So again, what's happening in the global simulation is that the reconnection is actually moving the plasma. The environment that's creating it is changing. In this PIC simulation, we are making the environment the same by continuing to allow plasma to flow in from the sides of the box and continuously feed this reconnection. So this is just to try and understand how different parameters create reconnection properties that we can then use those to map onto individual environments within the black hole simulation that might have different parameters for every one of those pixels and understand how particle acceleration is happening in each of those situations. And again, from frame to frame within the simulation, as the flare conditions are evolving and occurring, you will have pixels that have conditions that would create reconnection, and then later as the flare stops, those conditions themselves would evaporate.
Sophia, that was great stuff. So I was, of course, particularly interested in the PIC simulations.
Yes, so
towards
am I.
the end. So you showed that there are two regimes of reconnection, the strong guide field and weak guide field.
Yeah.
And they gave you quite different particle distributions, gamma energy distributions.
Yes.
And what impressed me most is that in one of those regimes, you could follow particles up to Lorentz factors 10 to the 5 and above. That is quite amazing, I
Yes.
think. I mean,
it is absolutely
did you have to
amazing.
do some
it is
special
quite
tricks?
amazing. So just to
Yeah.
emphasize what's happening here, because it's actually really interesting, is in a lot of particle and cell simulations that we're used to seeing, they happen in 2 dimensions, which means that all of the particles, as they're getting accelerated, they get trapped inside of these plasmoids and can't continue to accelerate to levels like 10 to the 5, right? And so what happens is all of the simulations I conducted for this project were 3-dimensional. This means that the particles are no longer trapped in the plasmoids. They can actually surf through different regimes of reconnection to kind of encounter different structures and then be accelerated by those structures. And what that means is that the partition of magnetic energy throughout the box is not divided evenly amongst all the particles, which is kind of what we think of as this this limit, this limit that we think of as like the sigma limit or like the magnetization limit in 2D, where all of the energy is kind of shared equally by construction. You don't really have a way to get around that. Here, it is very unequally distributed, kind of like our own economies, where the most accelerated particles are able to accelerate even more, and that's what ends up creating these extreme accelerations. Now you'll notice we don't create these extreme accelerations in conditions with strong guide field, and that's because it changes the balance of which specific acceleration process is happening. In reconnection, you can accelerate directly, which is, electric fields accelerate particles, and we get those electric fields exactly at the reconnection site. That's direct acceleration. You can also accelerate your particles through the changing magnetic fields that create electric fields that accelerate them. This is kind of this Fermi acceleration as they bounce off of these moving magnetic structures. And so what happens as you change to a higher guided field configuration is you're changing the balance of those two processes, where you're allowing, in 3 dimensions, you're allowing yourselves to have and experience more of this Fermi acceleration, and that really kind of pushes you over the limit. So direct acceleration kind of primes you into a position where you're energetic enough to make the most of the Fermi acceleration that proceeds.
Very nice. Thank you.
Don't see any further questions. So we can close it for now. Before we go, I just want to thank you all for coming. Thanks, Sophia, again for a nice talk. And I want to remind you of the timeline. We'll be taking a break for lunch and then reconvening later today. So be on the lookout for an email from me. And with that, we'll see you all later.